This is a very short video to get you started on Unit 7B. You're going to learn about ocean water chemistry, a little bit about the salinity of water, and the acid-base nature of water, or the pH. These two diagrams kind of summarize everything we're going to talk about in this unit. This is showing how the salinity of the ocean water, that is, how much dissolved salt is in the ocean water, can be affected by various things. Here we have icebergs falling off glaciers, and glaciers are freshwater ice. So if an iceberg falls from a glacier and then melts, it's adding fresh water to the ocean. And if it melts and adds fresh water, then the salinity of the ocean will decrease. Over here we have something called sea ice. That's a little bit different than how an iceberg forms. Sea ice forms directly from the ocean. It freezes. But when it freezes out of the ocean, it's fresh water only that freezes. The salts do not freeze into it. Sometimes it's called pancake ice. It only forms in very cold conditions. But if it forms, it's taking fresh water out of the system. So overall, the salinity of the ocean water left behind increases. On the other hand, if you melt sea ice, you're adding fresh water to the system, and so the salinity decreases. Another factor is runoff. That means water coming from rivers. Now, rivers usually have fresh water coming from them, so if we have a lot of precipitation and a lot of runoff from rivers, then we'll be adding a lot of fresh water to the oceans, and that will decrease the salinity in that area where the water's coming from. On the other hand, if we have dry conditions and runoff decreases, then the ocean salinity will rise. It'll become saltier. Finally, evaporation plays a role as well. This is pointing to the equatorial regions where evaporation is most likely. Evaporation does not take salts with it. Only fresh water evaporates. So the more evaporation that occurs, the saltier the water left behind becomes. So high amounts of evaporation increase the salinity of water. So this is the first concept you're going to learn. The second concept is about the pH, or the acidity of ocean water. This is showing the pH scale here on the left and time along the right. The line in dark red is showing the pH in the oceans over time and projected into the future as well. The pH of the ocean has been a little bit above 8 for a long time, and that is exactly how the organisms that live in the ocean like it. They want the pH to be 8. Or 8.1. Now you might know that the pH of neutral water is 7, and that's true. But in the oceans are a bit more basic than a 7, and that's the way that the marine organisms are accustomed. The other line that's in this graph, this yellow one, is dissolved carbon dioxide. And dissolved carbon dioxide makes the oceans more acidic. The more carbon dioxide there is in the oceans, the more acidic it is. And that's what this scale over here is showing. So you can see a very clear relationship that as dissolved carbon dioxide values increase, the pH goes down. And it's projected to a point where the pH might go as low as 7.85 by the year 2100. This would be devastating for marine organisms, in particular those that are made of limestone, because limestone will dissolve if the pH is too low. That's why people are very concerned about coral reefs disappearing in the near future. They cannot live in oceans that are more acidic than about an 8.05. Let's look at the learning outcomes for Unit 7B. There really are only two, and I think I kind of just summarized them, but go ahead and pause and write these down. The next 3 videos from the City College of San Francisco will explain each of these concepts in various ways.